Before defining the least common multiple, let us first prove two results regarding two integers a and b, which are coprime, meaning that their HCF is 1. Firstly, if a divides c and b divides c, then a times b also divides c. Secondly, if a divides b times c, it implies that a divides c. This second result is especially important and will be used several times in future videos. To prove this, since HCF of a and b is 1, we know from the extended Euclidean algorithm that there exist integers x and y such that a times x plus b times y equals 1. If we multiply both sides by c, we get axc plus byc equals c. For the first statement, a divides c means that we can write c equals k1 times a for some integer k1. b divides c means that we can write c equals k2 times b, where k2 is an integer. Now, c equals axc plus byc, which equals ax times k2b plus by times k1a. So we can take out the common factor a times b to get xk2 plus yk1 times a times b. This means that a times b divides c. For the second statement, if a divides b times c, it means that we can write b times c equals k times a for some integer k. Now, c equals axc plus bracket bc times y, which equals axc plus kay. So we can take out the common factor a to write xc plus ky times a. This means that a divides c, which completes the proof. Now, for integers a and b, we define the least common multiple of a and b as the smallest positive integer k such that a divides k and b divides k. We first prove a proposition which states that if a divides k and b divides k, then the LCM of a and b also divides k. This means that any common multiple of a and b must be divisible by the least common multiple. To prove this, let D equals the HCF of a and b. Then we can write a equals a prime times d and b equals b prime times d. We note that the HCF of a prime and b prime equals 1. Indeed, if c equals the HCF of a prime and b prime, then dc divides dA prime, which is a, and dc divides dB prime, which is b. Since dc divides both a and b, we know from the last video that dc must also divide the HCF of a and b, which is d. Since dc divides d, we know that c divides 1, so c must be 1. Now, let us set m equals d times a prime times b prime. We note that m equals a times b prime and also equals a prime times b, so a divides m and b divides m. We first claim that if a divides k and b divides k, then m also divides k. To prove this, we write k equals a times p, which also equals b times q. Then, a prime times d times p equals b prime times d times q. Cancelling d on both sides, we get a prime times p equals b prime times q. This implies that a prime divides b prime times q. Since the HCF of a prime and b prime is 1, we know from the previous proposition that a prime divides q. So q equals a prime times c for some integer c. So k equals b times a prime times c, which equals m times c. This implies that m divides k. Secondly, we claim that m is in fact the LCM of a and b, which from claim 1 would mean that the LCM of a and b must also divide k, which is what we want to prove. To prove this claim, let S be the set of positive integers k such that a divides k and b divides k. In other words, S is the set of common multiples of a and b. Then, the LCM of a and b is the minimum element of S, and m is an element of S. Now, if x is any element of S, we know from the first claim that m divides x. In particular, this means that m is less than or equal to x. So m is less than or equal to every element of S, meaning that m is the minimum element of S, which equals the LCM of a and b. So the proof is complete. Now we prove a result regarding the solutions to the equation ax plus by equals n. First, we fix positive integers a and b, and an integer n. Let d be the HCF of a and b. Assume that d divides n. Then all solutions x and y to the equation ax plus by equals n are of the form x0 plus t times b prime and y0 minus t times a prime for any integer t, where ax0 plus by0 equals n, a equals a prime times d, and b equals b prime times d. To prove this result, we know from the first video that d divides n implies that a solution to the equation exists, say x0 and y0. Let x and y be any solution. Then a times x minus x0 plus b times y minus y0 equals ax plus by minus ax0 plus by0, which equals n minus n, which equals 0. This implies that x prime, which is x minus x0, and y prime, which is y minus y0, is a solution to the homogeneous equation ax prime plus by prime equals 0, where the word homogeneous just means that the right-hand side of the equation equals 0. Now, let k equals a times x prime, which equals negative b times y prime. Then, a divides k and b divides k. From the previous proposition, we know that the LCM of a and b also divides k, where the LCM of a and b can be written as a prime times b prime times d. A equals a prime times d, and b equals b prime times d. So there exists an integer t such that k equals t times a prime times b prime times d, which equals t times a times b prime, and also t times a prime times b. Comparing these with the previous expressions for k, we know that x prime equals t times b prime, and y prime equals negative t times a prime. From the previous expressions for x prime and y prime, we know that x equals x0 plus t times b prime, and y equals y0 minus t times a prime. This means that we have written any solution xy in the desired form, so the proof is complete. We finish this video by giving an example of solving the equation ax plus by equals n. In this case, we want to solve the equation 5x plus 11y equals 1 for integers x and y. We first check that the HCF of 5 and 11 is 1, which divides 1, so a solution to the equation exists. A particular solution can be found using the extended Euclidean algorithm. Here, we are able to spot the solution x equals -2 and y equals 1. Also, the homogeneous equation 5x plus 11y equals 0 has the solutions x prime equals 11 times t and y prime equals -5 times t for integers t. This is because the HCF of 5 and 11 is 1, which implies that a prime is a and b prime is b. So the required solutions are x equals -2 plus 11 times t and y equals 1 minus 5 times t for integers t.